Jai Hind everyone. Myself Dr. Pankaj Goyal, working as an assistant professor in Ajay Kumar Garg Engineering College. Today we will discuss about pulse modulation, sampling theorem and Nyquist rate. In pulse modulation, as we know, here we use a train of pulses as a carrier signal. Instead of a complete analog signal, we are using a train of pulses as a carrier signal here, and this pulse modulation can be either analog or digital. In analog pulse modulation, the amplitude, width or position of the rectangular carrier pulse is changed in accordance with the modulating signal. So, we are changing the amplitude or width or position of the carrier, and they are known as pulse amplitude modulation, pulse width modulation and pulse position modulation respectively. First of all, we will discuss the pulse amplitude modulation. In pulse amplitude modulation, the amplitude of a constant width, constant position rectangular carrier is varied in accordance with the instantaneous magnitude of the modulating signal. Here we can see in this waveform that first of all at the top we have a modulating wave, then we have a train of pulses as a carrier signal, and then we have obtained the PAM signal, pulse amplitude modulation signal. And here we can see that whenever the pulse occurs, whenever the carrier pulse occurs, at that instant the amplitude of the modulating signal is taken and it becomes the pulse amplitude modulated signal. Here this is the PAM signal. Here is, as we can see here, as the amplitude of the modulating signal is varying, the amplitude of the PAM signal is varying accordingly. Here we can see so this is our pulse amplitude modulated wave. In pulse width modulation, as the definition says, the width of the carrier pulse is varied in accordance with the instantaneous magnitude of the modulating signal. And pulse width modulation is also known as pulse duration modulation or pulse length modulation. Now, when there is no message, that is Vm is 0, in that case the width of the pulse will be equal to the original width, and it is denoted by delta. For positive values of the message, the width will be proportionally increased by a factor of 1 plus Vm, where Vm is the instantaneous amplitude of the modulating signal. Similarly, for negative values of the message, the width decreases by a factor of 1 minus Vm. Also note that in pulse width modulation, as the amplitude of the pulse remains constant, therefore PWM is more immune to noise as compared to PAM. This is the advantage of PWM, because the amplitude remains constant in this case, so the effect of noise is minimized. This is the waveform for pulse width modulation. Here this is our modulating signal, this is our modulating signal. Modulating signal is also known as message signal. Then we have a train of pulses, which is your carrier, and then we are getting the pulse width modulated waveform. Here we can see the width of these pulses is varying. First of all, we can see here when there is no message, the width of all these pulses is equal to delta. There is no change in the width of the pulses when there is no message. Now, when the message is having some finite amplitude and it is positive, then the width of the pulse will increase. As the amplitude increase, the width will increase. Similarly, during the negative phase, when your message signal is in negative half cycle, the width will reduce from its original width. The width in this case will be lesser than the original width of the pulse. So, here we can see the width is very small compared to delta. So, here the width will be less than delta, here the width will be greater than delta, and here the width will be equal to delta. Next one is pulse position modulation. As the name suggests, in case of pulse position modulation, the position of each pulse is varied in accordance with the amplitude of the modulating signal. And also note that the pulse position modulation can be achieved from the pulse width modulation, as we can see in the next figure. Here we can see this is our message signal, then we have a carrier pulses, then we have a pulse width modulation PWM, and from PWM we have derived the ppm. Please note that in case of ppm, the amplitude and the width remains constant for all the pulses. In case of ppm, the amplitude and width remains constant for all the pulses, as is visible in the figure. The only difference will be in their position. Let us see here. When the amplitude of the message signal is positive, in that case the position of the ppm signal will shift to the right hand side. Here the position of the pulse will shift towards right hand side. Shift right. And when the amplitude is negative, the position of the pulse shift left. And when there is no message, then there is no shift in position. Here we can see, in case of PWM, the width increases and the trailing edge of this width, this pulse, from here the ppm pulse will start. So, if the width is more, if this width is more, the position of this ppm pulse is shifting rightward. And here, in case of this PWM, the width is smaller, this width is smaller. So, the position of this pulse will shift leftward, left side. here we can see in case of ppm, the position or timing of this pulse is proportional to this amplitude. Okay, when there is no message, Tp is 0 and the pulse will be equal to its original position. For positive values, the position will shift right by some function, and for negative values, the position will be proportionally shifted left. Okay. Okay. After discussing the pulse modulation, the next topic is sampling process, as this is very important process and it is related to the pulse modulation. So, we can say that sampling is a signal processing operation that helps in sensing the continuous time signal values at discrete instant of time, right. We know that an analog signal, a continuous signal, exists at every instant of time, and if we have to take the values of this continuous time signal at some defined instant of time, at some distinct instant of time, then that can be achieved by using sampling process. And whenever we take the samples, then the sample value will be equal to the value of the analog continuous message signal at that time. And this process can be conveniently performed using pulse amplitude modulation. Now, sampling theorem states that the sampling frequency or the number of samples per second should be greater than or equal to twice the maximum frequency component of the input signal. That is, if the rate of sampling is greater than or equal to twice the maximum frequency component of the message signal, only then at the receiver the sampled signal can be reconverted into the original signal faithfully. So, that is our definition of sampling theorem, that sampling rate should always be greater than or equal to 2 FM for it to be faithfully reproduced at the receiver. And the minimum value of this sampling is known as Nyquist rate. If the sampling frequency is less than the Nyquist rate, then the message signal cannot be reconstructed faithfully at the receiver. There is a numerical based on this concept of sampling theorem. Let us discuss this numerical to understand this concept further. A message signal made of multiple frequency components has a maximum frequency of 4 kHz. We have to find out the minimum sampling frequency required to faithfully reproduce the message signal at the receiver. Now, we know that the Fs is greater than or equal to 2 FM. So, it will be equal to 2 into 4 kHz. So, it must be greater than or equal to 8 kHz. So, the minimum value is 8 kHz. So, that is the minimum sampling rate that is required for it to be faithfully reproduced at the receiver. These are the references which I have taken into consideration while presenting this PPT. Thank you.